Welcome back everyone. So in last video I have shown you how to create the game, and in this video I will show you how to create the agent and how to train it to make it play the game on its own. So I have listed all the things that are necessary to make the agent play the game on its own, and I will implement them one by one. First we will see how to define the action, how the reward system is going to be, and then we will see how to define the state, and then we will go into how to create the agent and train it. So there are several things involved in creating the agent and training it. In that we will first see how to create a neural network, how the agent is going to use the neural networks, and we are actually going to use two neural networks for the training, and I will explain why exactly we use two neural networks, and I'm also going to explain how we are going to use the Bellman equation to set the target for the neural networks. And then we are going to create a memory for the agent, and the agent is going to use this memory to store the state, reward, next state, and the game status. And then we will see how to train the agent using epsilon greedy policy. Okay, let's start with action. So I'm going to define an action as a list with length 3, and all the elements in this list is going to be 0 except for one position which is going to be 1, and this one's position is going to decide which direction the basket should move. If the 1 is at the 0th index of the list, then we should move the basket to the left. If it is at the first index, then the basket should stay still. We shouldn't move the basket. If it is at the second index, then we should move the basket to the right. Now let's implement this. Okay, I'm going to define the action below the score. I'm going to say action equal to, first just give it a value of 0, 1 and 0. Now in each loop we need to specify which action we are taking. For now I am going to hardcode it like this. Later the agent will tell us which action to perform, and we will perform that action in the environment. So I'm gonna say 1 0 0 0 in each loop, move the basket to the left, and here we are controlling the movement of the basket using keyboard. We no longer need this, so I'm going to delete this, and instead I'm going to create a function that is going to perform this action, and this function is going to return two things: reward and game over status. This reward is the reward we get by performing this action, and game over status will give us the status of the game, if it is running or not. If we drop an egg, this game over status becomes true, else it remains false. So I'm gonna call the function as perform action, and we need to pass the action, and I'm going to write the function above here. So I'm going to say def perform action and action. Now just to make sure we don't get any error, I'm going to specify basket, eggs and score as global variables. So I'm going to say global basket, eggs, score, basket speed and egg speed. Okay, now we need to perform the action. If the 1 is at the 0th index of the action, we need to move the basket to the left, and we also need to take care of the condition that the basket won't leave the window. So we will move the basket to the left only if the basket dot left is greater than 0. In this case we move the basket to the left by saying basket dot x minus equal to basket speed. Okay, similarly if the 1 is at the second index of the action of 2 equal to 1, and the basket dot right is less than the width of the window, then only we move the basket to the right by saying basket dot x plus equal to basket speed. Basket speed. Okay, now we perform the action and we need to calculate the reward and the game over status and return it. Now this is how the reward system is going to be. If we catch an egg in the basket, we will give a reward of plus 10 to the agent, and if we leave an egg, we will give a reward of minus 10 to the agent. If nothing happens, the reward stays 0. So I'm gonna define a reward as 0 at the beginning, and game over status will be false. Now we need to check the condition of the egg. So we need to check this condition. We no longer need this one here, so I'm going to cut this and I'm going to paste it here. Okay, we go to each egg and check if there is any collision of the egg in the basket. If there is a collision, we increase the score by 1, and in this case we will give a reward of plus 10 to the agent. And if the egg falls down, in this case the reward becomes minus 10. and here it is game over, so I'm gonna say game over equal to true, and we need to return this value, so I'm gonna say return reward and game over status. Okay, now we need to exit this loop if the game is over, so I'm gonna say if game over is true, then I'm gonna say running equal to false. Okay, now in each loop we are hard coding action equal to 100, means in each loop the basket should move towards the left. When I run this script, the basket will automatically move towards its left. Let's see how it works. It should be like this. Now let's run this. Okay, as you can see, the basket automatically moved towards the left. I didn't touch the keyboard. Now I am gonna tell that the basket should stay still by saying action equal to 0 and 0. Now in this case the basket stays still, and if I do this by putting one at the second position, I'm saying the basket should move towards the right, and the basket move towards the right on its own. Perfect. Okay, we completed action and the reward system. Now let's look at what is the state of the environment. Okay, I'm going to define the state of the environment based on what action the basket is performing and what is the position of the egg with respect to the basket. So I'm going to make state as a list of length 5, and if the first position of this state list is 1, then it means the basket is moving towards its left. If the second position is 1, then it means the basket is staying still. If the third position is 1, then it means that the basket is moving towards its right. And if the fourth position is 1, it means that the egg is to the left of the basket, and if fifth position is 1, it means that the egg is towards the right of the basket. And to calculate what is the position of the egg with respect to basket, I am going to use egg.left and basket.left. So egg.left will give me the coordinate of the left side of the egg like this, and basket.left will give me the coordinate of the left side of the basket like this. If this egg.left is less than or equal to basket, it will become true when the egg is left to the left side of the basket, and this position becomes 1. And if the egg.left is greater than the basket.left, which is the case shown in this figure, then this becomes true and this becomes false, and this position becomes 1 and this position becomes 0. So that is how the state is going to be. For example, if the state list is like this 10010, it means that currently the basket is moving towards its left and the egg is to the left of the basket. Else if the state list is like this, it means that the basket is moving towards the right, since the third position is 1, and the egg is to the right of the basket since the last position is 1. Now let's implement this. Okay, I'm going to create a variable state, and I'm going to store the state of the environment in this variable, and I'm going to create a function that is going to return me the state of the environment, and I'm going to call it as a get state. And we need to pass this action as a parameter to this get state function so that we know in which direction the basket is moving. So I'm gonna say action, and I'm going to write the function above here. So I'm gonna say def get state and action, and I'm going to define basket and eggs as global. So I'm going to say global basket and eggs. First let's get the eggs, so I'm going to say egg equal to eggs of 0, and we need to calculate the state of the environment. It is going to be a list of length 5, and the first 3 positions in this list is going to be exact same things in this action. So I'm going to say action of 0, action of 1, and action of 2. And if egg.left is less than or equal to basket.left, it means that the egg will be to the left of the basket. This becomes true and it becomes 1. And if the egg.left is greater than the basket.left, it means that the egg is to the right of the basket. This becomes true, it becomes 1, and this becomes 0. Now I'm going to convert the state as a numpy array, and I'm going to return it. So I'm going to say return np.array of state comma t type equal to int, and I need to import a numpy module. So I'm going to say import numpy as np, and let's print the state to see how it looks like. So I'm going to say print state, Now let's run this. Okay, now you see the state is printed, and in each loop we are moving the basket to the right. That's why in all these the first three positions are 0 0 1, and initially the egg was to the right of the basket, that's why 0 1, and after the basket has crossed the egg is to the left of the basket, and the in rest of the positions the last two positions are 1 0. So it is working perfectly fine. Okay, the state is also completed. Now let's dive into agent. Okay, let's start creating the agent. I'm gonna define a class named agent, so I'm gonna call class agent, and let's define the init function, init self. For now I'm going to write pass here, later we will initialize all the variables when we need them. And remember that in each loop we hard coded the action, but later the agent is created, we will give a state to the agent and the agent will give us what action to make. So I'm going to write a function that give us the action to perform. I'm going to call it as get action self, and we need to pass the state to it. Later this agent will give us the action that we need to perform in the environment. And I'm also going to write a pass here, later we will implement it. And I'm going to train the agent using deep Q learning approach. So the agent is going to use neural networks to find which action to make based on the state. Now let's see how the neural network is going to be. Okay, this is how the architecture of the neural network is going to be. The number of neurons in the input layer has to be equal to the dimensions of the state. Since we defined state as a list of length 5, the number of neurons in the input layer is going to be 5. And you can customize the hidden layer like whatever you want. You can add multiple hidden layers, but a single hidden layer with 128 number of neurons worked fine for this game. And the number of neurons in the output layer has to be equal to the dimensions of the action. Since we defined action as a list of length 3, the number of neurons in the output layer is 3. Now let's say our state is like this. For example, let's say 1 0 0 and 1 0 means that the basket is currently moving towards its left and egg is to the left of the basket. We will give the state to the neurons, and then the neural network will output some values. I'm going to use ReLU as an activation function in the hidden layer, and after the forward propagation the neural network will output some values. And let's say the output of the neural networks are 0.54, 0.12 and 0.27. Now these are some example numbers, and what we do now is we create a list of size 3 and we populate it with zeros. And what we do is wherever the neural network has outputted the maximum value, we'll put a 1 in that position. In this case the first neuron has outputted a maximum value of 0.4, so I will put 1 at the 0th position of the list. So given this state, the neural network is giving us an output of 100, which is telling us to perform the action of moving the basket to the left. Now this is how the neural network will give us the action to perform in the environment when we give a state to it. Now this is all when the neural network is trained well. But initially when we give a state to it, the neural network will give some random number as output and we will get a random action. And the agent doesn't know what is the right action and what is the wrong action for a given state to compare that with the output of this neural network, and it won't be able to update the weights of this neural network correctly. So what do we give as a target to the output of this neural network? Now this is where the reward helps us, and we are going to use the reward to set the target of the output of this neural network. Now let's see how we are going to use the reward. So I have written down the outputs of the neural network on the side here. First thing what we do is we copy this output and set it as a target for this output of the neural network. And then what we do is we perform this action in the environment. Currently the neural network is telling us to perform the action of moving the basket to the left. So we perform it in the environment and calculate the reward by performing this action. For example, let's say we perform this action and we actually catch an egg. In this case we will get a reward of +10. Now what we do is wherever the neural network has given us the maximum output, we replace that value with the reward. So we will replace 0.54 with the value of 10. Now as usual we will compare these two values, calculate the raws and do the backpropagation, and the weights will be updated. Now after the weights are updated, when we give the state to the neural network, it will give us an output so that this value is maximized to match the 10, so that we will get 1 in the first position of the list. Now in this case it is correct because performing this action will help us catching the egg and we are getting a reward. Now let's see the opposite case. Let's say we perform this action and we actually drop the egg. Now in this case we will get a reward of -10. So we will replace the maximum value with -10. Now as usual we compare these two values, calculate the loss, and again we do the back propagation and the weights are updated. Now when we give the state to the neural network, and now it will give you output value in a way that this value will be reduced to match the -10, and as a result this value will be minimized and it won't be the largest value and some other value will be largest. So we won't get a 1 here, instead we get a 0 and we will get 1 in some other position. So we will avoid moving the basket to the left. Ultimately we will avoid dropping the egg. Since moving the basket to the left will leads to dropping the egg, we will avoid it. In this way the reward helps us in adjusting the weights of the neural network and helps us in getting the correct action to perform for a given state. Okay, all this makes sense now, but there is a better way to set the target for the output of this neural networks. Here we are just giving the immediate reward as a target. It means that we are just performing this action in the environment. We are calculating the reward that we are getting for now and we are directly setting it as a target for this output. But even though performing this action had given us a reward for now, it is not guaranteed that this action will help us in the long run. This action might be bad as the game continues. So we need to consider the long-term reward instead of just considering the immediate rewards. So what we will do is, instead of directly giving the immediate reward as a target, we will give a Q value as a target, and we will get the Q value from Bellman's equation. And this is how the Bellman equation looks like. This Qs comma A is the Q value for state S and action A. This Rs comma A is the immediate reward received after taking action A in state S, and this gamma is the discounted factor, and this term max A dash S dash comma A dash is the maximum Q value for next state S dash over all possible actions A dash. So we get this immediate reward by performing this action in the environment and calculating the reward, and this gamma is an hyperparameter. We can set whatever works good. Generally a value of 0.9 is chosen, and we need to calculate this term, which is the maximum Q value for next state S dash over all possible actions A dash. And this is where the second neural network comes into picture. We use the second neural network to find this term. For that, first we need to understand how the second neural network works. Okay, so what we do is we create two neural networks of same architecture. Let's say they are neural network 1 and neural network 2, and the agent will play several games. Let's say they are game 1, game 2, game 3, game 4, and so on. And in each game we will get several number of states, and we will pass these states into these neural networks and then train it. So for all these states the weight of this neural network is going to be updated. So the weights are going to be updated very frequently in this neural network 1. Now we don't touch the neural network 2, so the weights of this neural network 2 won't be changed very frequently. We only update the weights of this neural network 2 after a certain amount of time. Now this time might be after every 5 games or every 10 games or every 15 games, whichever works good for the game. For example, let's say we are going to update the neural network 2 after 10 games. So after 10 games is reached, what we will do is we will copy the weights from the neural network 1 and then put it into the neural network 2. Now in each game we will get several states, so we will pass the states into this neural network. This neural network will give us an action to perform. We will perform this action in the environment. We will calculate the reward, and then what we will do is, after performing this action, we will again calculate the state of the environment, which becomes the next state S dash. Now we will again pass this new state S dash to the neural network 2, and then this neural network will output 3 values, since there are 3 neurons in the output layer. And let's say that the values are P, Q and R. Now what we do is we take the maximum of this P, Q, R and then add it to this reward. Let's say P value is the maximum among these three, we will add P value to the reward, and this P value is exactly this term. And then what we will do is we will multiply this P with a discount factor gamma of our choice to decide how much this P value should contribute, and this value becomes the Q value. And now what we will do is instead of the immediate reward, here we will give that Q value as a target for this neural network. Now why do we even need a second neural network? Can't we just pass this new state into this neural network 1 itself and then calculate the Q value? From here we can, but it leads to a very unstable learning. Like I explained before, in each game there will be several states, and for all these states the weight is going to be updated in the neural network 1. So the weights in this neural network 1 are going to be updated very frequently. And let's say for one state the neural network 1 has outputted an action, and in the immediate next step that action might be wrong for that state and the weight will be updated like crazy. So neural network 1 will be very unstable. That's why to add stability to the training, we will create another neural network and then update its weight only for each 10 games so that it stays stable. It's like giving a reference to this neural network 1. It's like saying to the agent, hey, in a current game there might be several states, several things might go wrong, several things might change here, but remember that this is how things were 10 games before. And this actually helps in calculating the long-term rewards correctly, and it ultimately helps in playing the game for a very long time. Okay, I hope everything makes sense. Now let's create these two neural networks and implement all these things. Okay, I'm going to create the neural networks using PyTorch, so let's just import the necessary packages. Import torch, import torch.nnsnn, import torch.optim as optim, and then import torch.nn.functional as f. Okay, now I'm going to create a class for the neural networks. So I'm gonna call it as linear QNet, and it is going to inherit from the nn.module. Now let's create the init function, def double underscore init self, and this is going to take three parameters, which are input size, which is the number of neurons in the input layer, hidden size, the number of neurons in the hidden layer, and outputs is the number of neurons in the output layer. Now let's initialize everything in the parent class, which is nn.module, by saying super.init. And now let's create the layers. I'm gonna call the first layer as a self.linear1, which is equal to nn.linear of input size, comma hidden size, and then I'm gonna call the next layer as linear2, which is nn.linear hidden size, comma output size. Now let's create the forward function. Now this forward function is going to be called whenever we pass some value into this neural network. Let's say we pass x, and I'm going to use a relu as an activation function in the hidden layer. So I'm going to say f.relu of self.linear1 of x, and let's pass the x to the next layer by calling self.linear2 of x and then return the x. Now this will create our neural network. I missed a bracket somewhere here. Okay, good. Now, like I said, I'm going to use two neural networks. I'm going to call first neural network as DQ network and the second one as target network. So I'm going to say self.DQ network equal to this one. We are creating a object of this linear QNet, and since our state is a list of length 5, the number of neurons in the input should be 5. I am going to put 128 neurons in the hidden layer and number of neurons in the output is 3. Now this will create me a neural network with these number of neurons in the input, hidden and output layer. Now let's also create the target network by saying self dot target network equal to linear qnet of, it is going to have exact same structure as the neural network 128 and 3. Now let's also initialize some other parameters required to train this to neural network. So I am gonna say self dot learning rate. I am going to give a learning rate of 0.01 and then self dot optimizer. I am going to use Adam as an optimizer. So I'm gonna say Adam self dot this we are mainly going to update the weights in this DQ network. So I'm gonna say this DQ network parameters and then learning rate equal to self dot learning rate, and I'm going to use a mean squared error as a loss function. So I'm gonna say nn dot msc loss. Okay, now let's create the functions to train this DQ network and this target network. So I am gonna say def train DQ network of self. For now I am going to write pass here, later we will train them, and then def train target network self pass. Okay, now before training these two neural networks, so we need to talk about the memory of the agent. Let's discuss that. Okay, now this is how the memory is going to work. First I am going to create a DQ of some fixed size. For this game I have created a DQ of size 10 power 5. Now in the each while running loop, which is this one, I will calculate the state, action, reward, next state and the done. This done is the game over status, and then I put it into a single tuple and then I will push this tuple into this DQ. Now if you don't know how DQ works, when we keep on pushing data into it, it will store like this, and then when the number of data in this DQ reached its size, which is 10 power 5, and then we add a new data, what will happen is the data we have added at the beginning will be popped out. Simply the first data that is added, that will be popped out, and the new data will be pushed into the back. We will store this tuple in this DQ like this, and then in the same while loop parallelly we will take a random sample of 100 from this DQ. So we will randomly select some 100 data from this DQ, and then we will use that data to train the neural network 1 and neural network 2. Now why do we need to do this? Since we are doing these two activities parallelly in the same while loop, can't we just calculate this state, action, reward, next state, done in the loop and then directly pass them to this neural network 1 and neural network 2 and then train them? Well, we can do that, but there are several disadvantages involved in doing like this. Some of them are it leads to high temporal correlations and poor generalization, and it provides less diverse training data, which can slow down learning and reduces the agent ability to handle different situations. So this approach is not the best approach. That's why we use a memory, which is a DQ in this case. So we will continuously pushing these data into this DQ in each loop, and then we will randomly select 100 data and then use them to train this neural network 1 and neural network 2. And this memory is actually called as a replay memory for the agent. Now with this approach there are several advantages, and some of them are it reduces temporal correlation by providing diverse experience, it increases the data efficiency by reusing past experiences, and it reduces variance in updates leading to more stable learning. So that's why we will do this approach. Now let's implement all this. Okay, now let's create the memory. First let's define the memory size. So I'm gonna say self dot memory size equal to 10 power 5, 1 2 3 4 5, and then let's create the memory. I'm gonna call it as memory. Now I'm going to use dq as a memory, so let's first import it from collections. Import dq. Okay, good. Now I'm gonna say dq of max length equal to self dot memory size. Now this will create me a dq of size 10 power 5. Now let's also define the batch size. So I'm gonna say self dot batch size equal to 100. So in each loop we are going to randomly sample batch size amount of data from the memory and then use it for training. Now I'm going to create a function that will push the data into the dq. So I'm going to call it as remember, and we need to pass all the things we need to push into the memory. So we need to push state, action, reward, next state, and then done. Now we need to convert this into a tuple and then push it into the dq. We can simply do that by saying self dot memory dot append state, action, reward, next state, and then done. So we are putting all this value into a tuple and then pushing into the memory. Okay, this looks good. Now let's go down to our while loop. Here first let's create an object for our agent. I'm gonna simply call it as agent equal to agent. I believe we called it with this spelling. Yep, agent. Okay. Now what we do is in each loop first we calculate the state of the environment like this, and then we will ask the agent which action to perform. So I'm gonna say agent dot get action, and we need to pass the state. Now this get action is not implemented yet. I will implement it later, and then after getting the action we will calculate the reward and the game over status based on the action by performing it in the environment. Now after this we check for the game over status. If it is a game over, everything is over, and if it is not game over we will calculate the next state. So I'm gonna say next state equal to get state of action. So we'll calculate the next state. Now we need to push all this value into the memory. We can do that by saying agent dot remember state, action, reward, next state, and then the game over status, which is done. Okay, now we calculate all this thing and then push it into the memory. Now parallelly we need to train the DQ network by randomly sampling some data from the memory. So let's just do that. So we need to call the agent dot train DQ network. Now let's go above and implement this train DQ network. So this is the train DQ network. Now first we need to handle the case when the number of data in the memory is less than the batch size. So first I am going to create a variable called train size, and I am going to say minimum of length of self dot memory comma self dot batch size. So what this is going to do is if the size of the memory is greater than the batch size, we are going to consider the batch size as 100, else the entire memory is considered as a batch size. So that is the train size here. Now let's randomly sample some train size of data from the memory by saying batch equal to random dot sample self dot memory and then train size. So this will randomly sample some data from the memory, and let's separate them as states, actions, rewards, next states, and done. So I'm gonna say states, actions, rewards, next states, and then done's equal to zip of batch. Now let's convert all these into tensors. Okay, I have converted all these into tensors. Now to train this DQ network, we need to set the target for this DQ network using the Bellman's equations. So let's do that. First, let's get the predictions of this DQ network by saying pred equal to self dot DQ network, and we need to pass the current states. So we'll pass the states into the DQ network. The forward method in the DQ network will be called, it will do a forward propagation and we will get the predictions. Okay, to train this neural network, first we need to set the target for this neural network. So we need to find the Q value using the Bellman equation to set the target. So basically we need to calculate exactly this expression. Now, like I explained before, first let's create the targets and then copy the predictions value here. So I'm gonna say pred.clone. Now what we do is, so we replace the maximum value of this pred with the Q value like I explained here. So what we will do is, so we go one by one for each data. So I'm gonna say for a in range of the train size, and first we set the Q value as a immediate reward, which is rewards of I dot item. Now here we need to check a condition. If the game is over, we don't get to the next state, so there won't be a future Q values. And if the game is not over, we will get to the next state. In that case only we calculate the Q value based on the Bellman equation. So I need to check, if not duns of I, then we get to the Q value according to the Bellman equation. So I'm gonna say Q value equal to immediate rewards of I dot item plus the gamma value into the Q value of the future state. Now how do we get the Q value of the future state? By passing it into the target network. So first let's do that. So I am gonna say next pred equal to self dot target network, and we need to pass the next state into this target network dot detach. I am saying detach here because this target network is not a part of the computation graph. Now we need to get the maximum value of this next pred, which is going to be the Q value for the next state. So I am gonna say max next pred equal to torch dot max of next pred dimension equal to 1 of 0. So this will give me the Q value for the next state S dash, and then I need to multiply this here. Max next pred of I dot item. Now I also need to define the gamma value. Let me do that. Self dot gamma equal to, I'm going to give it a value of 0.9. Okay, good. Now we get the Q value based on this Bellman equation. Now we need to replace the highest value in this target with this Q value. So I am going to say targets of I, and to get the maximum value I am going to say torch of argmax. This will give the position of the highest value. Action of I dot item equal to Q value. Okay, we have set the Q value in the maximum positions place of the target. We did exactly this one, replacing this highest value with the q value. Now we need to calculate the loss and do the back propagation. Okay, first we need to clear all the gradients of the model parameters in the optimizer. So I'm gonna say self dot optimizer dot zero grad. Now we need to calculate the loss. So I'm gonna say self dot loss of targets comma bread. Now we need to do the backward propagation by saying loss dot backward. Now we need to update the parameters of the model. So I'm gonna say optimizer dot step. Now this will train the DQ network. Okay, everything looks good. Now let's go down to our loop here. So in each step we will push all this into the memory and then we will train the DQ network. And we also need to update the weights of the target network for every 10 games. So first let's create a variable that keeps track of the number of games that has happened. So I am gonna call self dot n games, standing for number of games, self dot n games. First initialize it with 0, and if there is a game over, then the number of game increases by 1. So I am gonna say agent dot endgame. Endgames, is it endgames or endgame? Endgames. Endgames plus equal to 1. We don't get out of the loop here because we need to train the agent on several number of games. Instead we will reset the environment. I will implement the reset function later. For now let's do this, and then if agent.endgames %10 equal to 0 means for every 10 game we will update the weights of the target network by saying agent.train target network. Okay, now let's implement this train target network. So let's come above here. We simply train the target network by simply copying the weights from the DQ network. So I am gonna say self dot target network dot load state dist self dot DQ network dot state dist. Okay, this will copy the weights from the DQ network and then loads it into the target network. Okay, now everything looks good. Also, I have checked that I have made some spelling mistakes. I have corrected them and everything looks good here. And just to make sure we don't get any error, I'm gonna replace this pass here in this get action method with a left moving action 100. Now let's run this and let's see the result. Okay, the game is functioning well. Actually it is training now, but we haven't implemented the get action method to do an actual training. So everything works without an error. That's good. Now I'm going to stop here for this video. We have completed the neural network, how the agent is going to use the neural network. I have explained why we use the two neural networks, the Bellman equation and the memory of the agent. And in the next video let's do the actual training using the epsilon greedy policy and then visualize the results.